So hello everyone, this is lecture 21 for the classical physics. In the last lecture we have discussed about the Lagrangian, we seen some questions and we are having a very good idea now what is Lagrangian, how we are getting the equation of motion. Okay, we discussed some examples. Now today we will discuss some theory first about the generalized momentum. See, if we have the generalized coordinate and we discussed that if generalized coordinates are changing with time, then we will have generalized velocity. Then ultimately, if we have velocity, then we have the generalized momentum, because there will be some force and then there will be momentum also. Okay, so today we will see what is generalized momentum. So in the by the definition, we define generalized momentum as means generalized momentum to any particular generalized coordinates will be del L by del Q J dot. Okay, so this will be your generalized momentum corresponding to Pj. Now in 1D problem we can see this proof. See, in the 1D problem we can define the Lagrangian in this form. This is kinetic energy minus potential energy, x dot square Vx. Now see, if you find the del L by del x dot, you will see you will get here mx dot and this will be 0, and this is nothing but mv. This is your momentum in extraction. So that's how you can see that this del L by del x dot represents the momentum. Same if you have in 2D plane, and 2D plane you are representing in the r and theta form, the polar form you are using, because this is a plane motion. So L will be represented by this formula, half m r dot square plus r square theta dot square minus vr. This is velocity in the polar coordinates. Okay, so this is kinetic energy minus potential energy. Now see, if you have the motion in 2D, then you will have two kind of momentum, that is angular momentum and the linear momentum, because something is moving inside the polar coordinates. So we'll discuss about this. I will tell you how the coordinates are there and how we get this velocity. Just here, just remember this, that we use this formula, and velocity is this and kinetic energy is this. Okay, so PR will be del L by del R dot. So first find the derivative with respect to R dot. You will get mr dot and this will be 0, and this is nothing but linear momentum. Again, let's find the with respect to theta dot, because we have two variables. So p theta will be del L by del theta dot. So this will give you, this will be 0, and this will give you mr square theta dot. So remember this formula very well. This is angular momentum. So they are giving the very correct results to us, this formula. So we will say that this formula represents the generalized momentum. So that's how we came to this conclusion. Now we can write the kinetic energy in terms of the momentum also. Means if you want to write this kinetic energy in the polar coordinates, then how will you write? R dot is PR divided by m. So right here PR square divided by m square, and here theta dot square. Theta dot is nothing but p theta divided by mr square. So it will be p theta square divided by m square r4. So they will cancel out and you will get this formula for kinetic energy in terms of the generalized momentum. So it will be PR square divided by 2m plus p theta square divided by 2mr square. So that's how you can represent the kinetic energy in terms of the polar generalized momentum. Okay, so remember this formula, very important. Now see, if you have Lagrangian equation of motions, means let's just find this momentum with respect to with the help of the Lagrangian equation. So what result this gives us? So we know this is our Lagrangian equation. So this del L by del Qj dot is nothing but Pj. We defined this here. So now this dPj divided by dt is nothing but del L by del Qj. So from here we can say that means change in generalized momentum, Pj dot is represented by del L by del Qj. So just remember this result also. This represents the change in momentum, because if there will be some force, then there will be change in momentum also. So this is represented by del L by del Qj. So we'll see about the generalized force and all. So just here for now, just remember this result. Now there is a very important thing, that is cyclic coordinate, to use the Lagrangian. So what are cyclic coordinates? Generalized coordinates that do not appear explicitly in the Lagrangian of a system are called cyclic or ignorable coordinates. So what is the meaning of this statement? It means that we represent the coordinates q1, q2, q3 and up to n. We have generalized coordinates. So if any particular coordinate is not appearing there, means if q2 is not there, we have q1, q3, q4, then q2 is nothing but generalized coordinate, cyclic coordinate, because that is not appearing explicitly, means it is not present individually there. So we call that coordinate as cyclic coordinate or ignorable coordinate. And it is possible that if q2 is not there and q2 dot will be there in the generalized coordinate, So that is a possible condition. Here also we will call q2 as cyclic coordinates. So however, their velocity component may appear in the Lagrangian. So let's see what I'm trying to convey here. That if these are your coordinate systems, means generalized coordinates are these q1, q2, q3 up to qn, then it is possible that q3 is not present in the Lagrangian. Means when you write the Lagrangian equation for these generalized coordinates, then maybe in the Lagrangian you won't have q3, q1, q2, q4, and that's also this q3 is nothing but cyclic coordinate, and because L is independent of this. Now it is possible that q3 dot is present but q3 is not there, so still q3 is cyclic coordinate. So if q3 is not there, then if you find the partial derivative of L with respect to q3, you will get 0, that is for sure. Now see, in the Lagrangian equation, let's substitute this value for the cyclic coordinates. What we will get? So this del L by del q3 is 0. So this will give us del L by del q3 dot is nothing but p3. This is momentum r. We already defined this. So dp3 divided by dt is equal to 0. So p3 should be constant. So this is the result. Means if you are having any cyclic coordinates, then momentum corresponding to that, means generalized momentum corresponding to that, will be conserved, and this is called the constant of motion also. Okay, so what is the result? That is, generalized momentum corresponding to a cyclic coordinate will be a conserved quantity throughout the motion of the system. So remember this result. This is very important result. Now let's say in the brief, if qk is any cyclic coordinate, then del L by del q will be 0 and pk will be constant. Okay, this is the result we find from here. So if qk is any cyclic coordinate, then momentum corresponding to that, the generalized momentum corresponding to k, will be constant. Now let's see some things. This is what? This is our Lagrangian for a cylindrical coordinate system. Okay, so I will tell you more about this. Just here remember that in cylindrical coordinate system, you represent velocity by this. Okay, and this is your potential energy. So kinetic energy minus potential energy represented by the Lagrangian. And in cylindrical coordinate system, we represent coordinates by s, phi, z. So I will tell you more about this. Just here remember this formula only. Now see, we have s dot here, s here. We have z dot here, z here in the Lagrangian. We have phi dot, but we don't have phi in the Lagrangian. So what is the meaning of this? Means phi is our cyclic coordinate because phi dot is present but phi is not there. So what is the meaning of this? Means del L by del phi will be 0 because it is independent of phi. Then p phi, this generalized momentum corresponding to phi, will be constant. So this is the result we used. We means what we proved here. So we can direct if it is independent of this, we don't need to write this. We can directly say that p phi will be constant. So most of the time we write direct this result. So we need to remember that we get this result from the Lagrangian. Okay, so p phi will be constant. So let's see some questions based on them, these results. So Lagrangian of a system described by 3 generalized coordinates is, so Lagrangian of a system is given with these coordinates. So Lagrangian is half m q1 dot square plus q2 dot square plus m q1 dot q2 dot plus k q1 dot q3. Okay, so where m, capital M, k are positive constants, then as a function of time, so there were options there, I didn't write them. So options were that if we need to tell that how q1, q2, q3 are evolving with time, are they constant with time or they are evolving linearly with time. So we don't need to find the relation between q1 and time, or q2 and time and q3 and time. Okay, so let's see how can we find that. First, by seeing the Lagrangian, we can say that it is q1 dot here but q1 is not there, so q1 is cyclic. q2 dot is here but q2 is not there, so q2 is also cyclic. And q3 here but q3 dot so q3 is there. Okay, so it is of q1, q2, q3, so q3 is not cyclic, but q1, q2 are cyclic. So if q1, q2 are cyclic, then we know p1 will be constant and p2 will be constant, and p1 is nothing but del L by del q1 dot. So you will find the derivative. You will get m q1 dot plus m q2 dot, and this will be k q3. So this will be conserved from the result we already proved. So this is constant, and if p2 is all, means q2 is also cyclic, so p2 will be del L by del q2 dot. So this will be constant also. Find del L by del q dot, del L by del Q2 dot from here. So it will be this M Q2 dot capital M Q1 dot. So this will be constant also, equal to constant. Now see P1, P1, P2 we already find. Now for the Q3, we know this is not cyclic, so it will satisfy the Lagrangian equation. So let's find the Lagrangian equation for the Q3. So it will be del L by del Q3 dot and del L by del Q3, and substitute in the formula. So d by dt of del L by del Q3 dot. So what is the del L by del Q3 dot? It is independent of Q3 dot, so it will be 0. So d by dt of del L Q3 dot will be 0, and it is minus del L by del Q3. So del L by del Q3 will give you k Q1 dot. So now the equation will be this minus this. So 0 minus k Q1 dot will give you Q1 dot equal to 0. Now you have this. This is nothing but del Q1 divided by delta t equal to 0. From here you can see that Q1 will be constant. Means Q1 dot is 0, means dQ1 divided by dt means Q1 will remain conserved. So Q1 will be constant. So we have this result. Now let's substitute this result here. Q1 dot is 0. Then we will see that means this whole term is constant. So this is 0. Now this is equal to constant. So we will write that this mQ2 dot plus 0 equal to constant. From here you can see that Q2 dot will be, m will go this side and it will again be constant. So this is dQ2 divided by dt. So dt will go this side, so you will get Q2 equal to C1t plus C2. Now this is a linear equation, means equation of a line. Means Q2 is evolving with time in a linear way, okay? And Q1 is constant throughout the time. Now let's find for the Q3. So let's substitute these values here. So Q1 dot is 0 and Q2 is C1t plus C2. Means you can write from Q2 dot is C1. So Q2 dot is C1 and Q1 dot is 0. So this is MC plus K Q3 equal to constant. Then from here you will say that this constant will go this side minus, then K Q3 is again constant, and then Q3 will again be a constant. So you will get Q3 equal to constant. So this will be your evolving of these coordinates. So Q1 will be constant throughout the motion, Q3 will be constant throughout the motion, and Q2 will evolve with time linearly. So these will be your answers. This was a very good question. Now there are some results you need to see. Means different coordinate systems we have in the mathematical physics. If you already seen my lectures, then there in the vectors lectures I already told you what are spherical coordinate system, cylindrical coordinate system, how we convert them, and all the things you need to understand about the coordinate system we already discussed there. But here I will just give you an idea how we do these things and how you can see the Lagrangian in these coordinate systems. So in the Cartesian coordinates we have Lagrangian is this: half m x dot square y dot square z dot square, because this represents the velocity across x, this is velocity across y, and this is velocity across z. So vx square plus vy square plus vz square will give you v square. So this is kinetic energy minus potential energy. So you have this thing in the means in the Cartesian coordinates. Now motion is in 2D, means we know we describe the polar coordinates for the 2D motion when a particle is moving or mass is moving in the 2D system, in the xy plane, let's say. Then we represent this motion can be represented in the r theta form. So how? See, if this is your particle and this is moving, so now this is your radial direction. So at any point, if it is moving like this, so this r is not fixed. If it is at this point, then r cap will be in this direction, and theta is changing in this direction, so theta cap will be in this direction perpendicular to this. Now if it was here, then r cap will be in this direction, theta cap will be in this direction. So that's how they can change, okay? So from here we can see that this x component, can we find it? It is nothing but if this is r, then this will be r cos theta and this will be r sin theta. So you can write x and y directly from here. X will be this and y will be this. But if you need to see, means you need to find the Lagrangian, so you need the velocity. So for velocity of this particle, it will be vr and v theta. So vr r cap and v theta cap. So we need to find the velocity in both these directions. So how can we find? So what is the velocity in radial direction? It means how this r is changing with time in this direction. So that is vr. So this is changing in r with time, so we will write it r dot. So VR is nothing but r dot r cap, in direction r cap. Now we need to find this, how this theta is changing in this direction. So we need to find this theta dot. So see, if this is changing in d theta, and this we fix this, means the benefit of the perpendicular or the orthogonal axis is this, that we place one thing constant and take the second thing. Means first when we find this radial velocity, we put theta constant and we find the r dot. So we find the VR velocity. Now to find this theta velocity v theta, we put this r constant and we move this side. So we move the d theta, and this radius is r, means radial distance is r. So this distance will be r d theta. This distance will be r d theta, and it is changing with time, so we'll write r d theta by dt. So this is nothing but r theta dot, theta cap. So this will be your velocity along the v theta direction. We call this radial velocity and this called the angular velocity. So v theta was r d theta divided by dt, and that's how we get this r theta dot theta cap. So that's how you can find this VR. Now the magnitude of VR will be r dot square plus r theta dot square. So that's how you can find the Lagrangian for this system. L will be half m r dot square plus r square theta dot square minus VR. So in polar coordinates you write Lagrangian in this form. Now let's see if now this system or the particle is moving in 3D. Means it is in this polar coordinate, now it moves in the 3D. So how you can denote that motion? So see, this motion can be represented by the cylindrical polar coordinates. Okay, it is mostly same, means we have this 2D motion, now we are in moving 3D, so we will, like it is a disk, okay, r theta, and you are moving in this z direction, then it will be a cylinder formed. So you can represent that motion in the cylindrical coordinates. In cylindrical coordinates, this is just a expansion of polar coordinates in the 3D. So in the means r theta z, this will be your coordinates, means at any point it will be r theta and z. So in the cylindrical coordinates we represent r by s, theta by phi, and z will be z. Means see here, this xy plane is same as here, the polar coordinates. Now the motion is in the z in the z direction or the 3D system. So this is your r represented by s, this is your theta represented by phi, and this is your z. Now at any point this will be your distance s. At any point here this will be your distance s. So s cap will be changing in means direction of s cap will be radially outward, and for phi it will be going inside the paper, going this direction, and z cap will be changing direction in this z direction, so this will be in this direction, and this phi cap is nothing but perpendicular to s cap and z cap. So at any point you can find all these three directions. Now velocity is along these three directions, so you need to find the velocity now in these three directions. So see, for the s, the velocity will be s dot, as we find it here, the r dot. For the phi, this will be same, the changing in this direction, so this will be d phi, and r s d phi divided by dt will give you s phi dot. So this will be your s phi dot for the phi v phi, and for the z direction it will be changing in z direction, okay, with time, so it will be z dot. So this will be your velocity in the cylindrical coordinate system. This is s dot s cap plus s phi dot phi cap, this is your phi cap, and this will be z dot z cap. So this will be your velocity. So how you can find the Lagrangian now? So velocity will be s dot square plus this square plus this square. So that's how you can write the Lagrangian in the cylindrical coordinate system. Okay, half m and square of all those terms, vs, v phi and vz minus potential energy. Now let's see an example based on this. A point mass m is constrained to move on an inner surface of a paraboloid of revolution x square plus y square equal to az, where a is greater than 0 is constant, where it spirals down the surface under the influence of gravity along z direction. The angular speed about the z axis is proportional to. So it's like paraboloid is what? It's look like this. Means you made a parabola, then you revolve this around, then you will get a paraboloid. So a particle is restricted to move on this paraboloid, and it is spiraling down. Okay, so it is moving in this system, means this like this spiral motion. So and the equation is given x square plus y square equal to az. So this is moving under gravity downside. So we need to find the angular speed about the z-axis. So we need to find the phi z, means phi dot z actually. So it's like means body is moving downside, so this is our z-axis, so it is revolving around z-axis. So we need to find this angular velocity phi, okay, phi dot actually, okay. So around this z-axis, so phi dot we need to find. So phi dot will be proportional to what? Independent of z, proportional to z, or z inverse, or z minus 2. So let's see how we can find this. So remember this thing, whenever you get this kind of thing, x square plus y square, then always use the cylindrical coordinate system. So let me tell you why. Because in cylindrical coordinate system, you know, this x and y is nothing but x is s cos phi and y is s sin phi. So if you substitute here s cos phi and s sin phi, you will get x square plus y square equal to s square. So this will be a very simplified thing, means x square plus y square will be written as s square. So now x square plus y square will be s square equal to az. Now we have very simplified equation. We have two variables only, because there is only one constraint equation and particle is 1, so degree of freedom will be 3 minus 1 2. So that's how z and s are your systems, means generalized coordinates. Now how you can find the phi dot? So for that you need to use the Lagrangian, of course. So what is Lagrangian? I already told you, for the cylindrical coordinate system, this is your Lagrangian. Now you know from there s square equal to az, we already seen this is your constant. So in place of z you will write s square by a, and in place of z dot you will write 2s s dot divided by a. So this will be your z dot, this is your z. So substitute here and find the equation in terms of s only. So after substituting these values you will get this thing. And now seeing this Lagrangian, see phi dot is present here, s dot is here, s is here, but phi is not there. So phi is not there, but phi dot is here. So phi is cyclic, okay. So phi is cyclic. Now what is the result of this? If it is cyclic, then p phi, this is momentum, generalized momentum, will be constant. So del L by del phi dot will be constant, and this is nothing but find this term from here. This will be ms square phi dot. So this will be constant. Now from here you can find this phi dot. This is the angular velocity which you need to find actually. So phi dot is nothing but c1 over ms square. Now in place of ms s square, so s square is nothing but az, so write it here. Now this is c1 over maz. So see, this phi dot is inversely proportional to z, means directly proportional to z to the power minus 1. So this will be your answer, C. Now try to solve this question. We will discuss this question in the next lecture. A particle of mass m moves inside a bowl. If surface of bowl is given as z equal to 1 by 2 a x square plus y square, where a is constant, then find the Lagrangian, find equation of motion, and find angular velocity if it is constricted to move at a fixed height z naught from xy plane. So again you are getting x square plus y square here, so use the cylindrical coordinate system and try to solve this question. Okay, this is very easy. So we'll meet you in the next lecture. We'll discuss some more questions. Till then, thank you everyone. Bye bye.